Have you ever stopped to think what a falling apple, a rocket launching into space, and you just standing perfectly still all have in common? Well, it turns out they're all playing by the same surprisingly simple rule. Today, we're going to decode Newton's second law. And trust me, by the time we're done here, you'll see the forces that shape your world in a totally new way.
All right, so first things first, we've got to bust a pretty big myth. Most of us tend to think that if something isn't moving, there's not much going on, physically speaking. But that couldn't be more wrong. Okay, take a look at this soccer ball. It's just sitting there, not going anywhere. So here's a question for you. Are there any forces acting on it right now? At all? Just think about it for a sec. Is anything pushing it or pulling it? Now, you might be tempted to say no, but the answer is a huge yes. In fact, there's a constant invisible battle of forces happening. You've got gravity, which is always pulling the ball straight down toward the center of the Earth, but at the exact same moment, the ground is pushing back up with the exact same amount of oomph. In physics, we have a name for that upward push, the normal force. So what happens when you have a perfect cosmic tug-of-war like this? Well, they completely cancel each other out. Gravity's downward pull and the normal force's upward push are in a perfect stalemate. This balanced state means the total, or net force, on the ball is zero, and that is the secret to why it stays perfectly still. And this whole idea of net force, you gotta get this, because it's the key to everything. It's the leftover force after you add up all the pushes and pulls. If the net force is zero, things are, well, kind of boring. An object at rest stays at rest. But the moment that balance is broken, the instant there's a net force that isn't zero, well, that's when things get interesting. That's when you get a change in motion. You know, this idea that unbalanced forces are what make things move wasn't just a random observation. It was brilliantly captured and basically turned into a recipe for the universe by one of the greatest minds in history. So way back in 1687, this guy, Sir Isaac Newton, he publishes this absolute game changer of a book called Principia. Inside, he lays out 3 laws of motion that totally revolutionized how we understand the universe. We're going to focus on that second law because that's the one that gives us the mathematical recipe for motion. And this is where the pure genius of it all lies. Newton's second law creates this beautiful, simple bridge between 3 really key ideas: the force you use, the mass of the thing you're using it on, and the acceleration, the change in motion that happens because of it.
And this brings us to, well, it might just be the most famous equation in all of physics, F equals ma. So let's crack it open and look at each of the ingredients to see how this powerful recipe really works.
Okay, let's meet the players. First, you've got F for force. Super simple, any push or pull. We measure it in newtons. Next up is M for mass. Now this is key. It's not just weight, it's the amount of stuff in something, which gives it inertia. You know, its natural stubbornness about being moved. We measure that in kilograms. And finally, A for acceleration. This is any change in velocity, speeding up, slowing down, even just turning a corner. It's all about how quickly your speed changes.
So, how do they all relate? It's actually really intuitive. Think about pushing an empty shopping cart. If you push it harder, that's increasing the force, it's going to speed up faster. Make sense? But now, what if you load that cart up with groceries? You've increased its mass. If you give it the exact same push as before, it's going to accelerate way, way slower. That's the core relationship right there. More mass needs more force to get the same acceleration.
And so, here we are, the law itself. The net force on an object is simply equal to its mass multiplied by its acceleration. Simple, elegant, and it explains pretty much everything that moves. All right, enough theory. Let's put this law to the test with a real-world puzzle that I guarantee you've experienced, but maybe you never knew how to explain with physics.
So why do you get that weird, brief sensation of feeling heavier when an elevator starts to go up? You know, that little squish feeling? It's not just in your head, and Newton's second law tells us exactly what's going on. Let's walk through it. Just like that soccer ball, when you're in an elevator, there are 2 forces on you: gravity pulling you down and the elevator floor pushing you up. That's our old friend, the normal force. Now, to get you to accelerate upwards, there has to be a net force pointing up. That means the upward push from the floor has to be stronger than the downward pull of gravity. And that extra push, that's exactly what you feel. Your brain just interprets that stronger normal force as you getting heavier.
We can even attach some math to it. See, when you're standing still, the floor pushes up with a force equal to your weight. And your weight is really just a force, your mass times the acceleration from gravity, or mg. But when the elevator accelerates up, the floor has to do that same mg just to hold you. Plus, it has to add an extra force to get you moving, and that's the ma from Newton's law. So the total push you feel is mg plus ma. This chart shows it perfectly. At rest, you feel 100% of your normal weight. When you accelerate up, that normal force gets bigger, and maybe you feel 120% heavier. And hey, the opposite is true too. When the elevator starts going down, the floor doesn't have to push up as hard, and you get that little stomach drop sensation of feeling lighter for a second. So look, the really big point here is that this isn't just a fun fact for elevators or shopping carts. This single law has a significance that is, well, it's truly cosmic. It's kind of mind-blowing when you think about it. In the entire known universe, physicists have found just 4 fundamental forces that run the whole show. And Newton's second law is the universal framework for understanding how all of them behave, from the tiniest subatomic particles to the biggest galaxies. Every push and pull you've ever felt is just one of these forces in action. And it is absolutely no exaggeration to say this. When Newton published his laws of motion, it changed the world. It gave humanity a predictable, mathematical toolkit to understand the physical universe for the very first time.
So just let that sink in for a moment. One simple rule, F equals ma, describes both an apple falling from a tree and a planet orbiting a star. It's a stunning example of how a simple, elegant idea can unlock the deepest secrets of the universe. And it leaves us with one heck of a thrilling question. What's the next simple rule out there just waiting to be discovered?